Good morning, everyone. So welcome to the course Transformer Methods, Factoring 1, which is the ECS 301. And my name is Hongren Li. So I will be the instructor of this course. So I'm very happy to learn this course with you together this quarter. And here is the agenda for today. So since this is the first lecture, and I will go over the syllabus with you. First, just to make sure you know the contents of this course and also know the policies. And then I will directly go to the textbook I will cover and talk about the two topics. So first I will define two types of signals, and then I will talk about some basic properties, which is the transformations on the independent variable of signals. So for the first one, I will cover the mass representation of a signal, and then talk about the energy and the power of a signal. So for the transformations, I will cover the time shifting, time reversal, time speed, and then talk about the periodic signals and the odd and even signals. So it's okay if you are not familiar with these concepts, so we will go over them one by one later. So let's first talk about the syllabus. So I guess everyone has the syllabus now. So I will just take some points out and make you pay attention to them. So the first thing is, so we have, for this course, so we have 2 lectures every week, which is Monday and Wednesday, from 8 to 9:20 a.m. in this room. And at the same time, on every Friday, so we will have a recitation section, or quizzes or midterms, also on Friday, the morning, from 9 a.m. to 10:50 a.m. So same in the same room here. Okay, and I have my email here on the syllabus and the phone numbers, so you are welcome to contact me via the email or phone calls or text messages for any question you have. And my office is the Boston 604. I would like to put an 8 here because there's another dot tag with 604, so just the next dot is 6048. And I have my office hours following the lectures right away. So like our lecture ends Monday, Wednesday at 9:20. My office hours starts at 9:30 and to 10:30 every Monday and Wednesday morning. Okay. Regarding the course contents, so this course will basically cover some basic concepts relating to some signals and systems, and we will learn how to model them, so use some mathematical formulation to model them and do some analysis. So, and we know there are a bunch of signals and systems around us, and we would like to use mathematical solutions to of these general models. So we want to learn some basic mathematical tools like the convolution, Fourier series, Fourier transforms, and we know how to analyze them. So in particular for these signal systems, we are interested in the linear time invariant systems, as I will define in the next lecture. So our textbook is this one. So the signals and the systems, second edition by Alan Oppenheim and Alan Wilsky with Hamid Nawal. So I ordered this textbook in the bookstore already. So just to make sure everyone gets one copy. Because we use this textbook for lectures and homeworks, assignments. And to succeed in this course, you must attend this lecture, and you also need to read the materials in this textbook, and also do the homework and practice a lot. So we will use Drexel's Blackboard Learn system to manage this course, including the homework assignment solutions, and midterm solutions, and also the quizzes. And also your grades will be posted there. So another thing is to make sure your Drexel email is set up properly, so that you can receive the announcements properly. So I will see the previous on and Drexel account. Drexel email account. So what's the format of this course? So we will have, as I said, we will have lectures and recitation. So in lectures, we will basically cover the concepts and the theorems, but due to the time limit, we will have very few examples in the lecture. So therefore, we will put the practice in recitations. So we review the concepts and the theories covered in the lecture, and give you focus more on the practice. And we will have quizzes and midterms in the same time for in the recitation section. So that's why the attendance to the recitation is required. So just make sure you arrange properly for your time, because every recitation there will be either a quiz or midterm, and there's no makeup for them, as I will say later. Okay, so next is about the grading policy. So we will have non-homework assignments, and I will drop the two lowest ones. So that's why there's no makeup, no late summation for homeworks. So 20 points for homework. And we also have 20 points for the quizzes. So there will be 7 of them, and each during the recitation section. And I will drop the lowest one. So you are allowed to, like, if you cannot come, there will be at most one time. And we will have 2 midterm exams. So 30 points in total, which means 15 points each. And then we will have the comprehensive final exam, which will cover all the materials in this lecture, in this course. So 30 points for final. And I will let you know the date and the location if it's assigned by the university. That's why you must have your Drexel email account set up properly to receive the announcement. Okay. And all homeworks will be assigned on each Wednesday and due 1 week later, at the beginning of class of the following Wednesday. So you're allowed to discuss each other with the homeworks, but all solutions you submitted must be independent, your work. And no copying solution is allowed because that will be viewed as cheating, and you will be given a 0 for that assignment, or even fail this course. And since I will give unnecessary equations to the quizzes and the midterms, so all the quizzes and the midterms are close to books and notes. You don't need that. And but you're welcome to bring a basic calculator to help you in the calculations. But I imagine there will be no difficult calculations. And no other electronic devices are allowed in the quizzes and the midterms or the final exams. Okay, and based on this, and the numerical score will be used to assign you a letter grade following this table. And possibly I will make a scale up so that you will have a better letter grade, but maybe not scale at all. But I will definitely not scale down, so don't worry about that. So okay, now let's talk about the course schedule. So as I said in the overview of this course, so I will basically follow the order of this book, and we will cover the chapter 1 up to 5, chapter 5, and if we have time, we can cover a little bit in chapter 7 on sampling. And so, like in chapter 1, we will cover basics about signals and systems, and then in chapter 2, we will talk about the linear time invariant systems, and then talk about the convolution. And chapter 3, we will talk about how to use the Fourier series to represent a signal. And following that, we will talk about the Fourier transforms, which include the continuous time and the discrete time. Okay. So as I said earlier, so we have the general class policy here. So cell phones must be turned to vibrate, and no texting or phone calls are allowed. And your computers and other electronic devices is limited for use, only for taking notes or computation exercise. And it's strongly recommended to attend every lecture. And actually, I would like to, take some attendance sunshade maybe for you to require you to attend the lectures, because it's not easy to get success for this course if you don't attend the lectures. And as I said, the attendance to recitation is required, but now the lecture attendance is also required. So if you don't have some excuses like out of your control, then I will take some points off if you don't come to the lectures. Okay? And as I said, no makeup exams, no late submissions. And if you miss one for the exams and with a reasonable excuse beyond your control, just let me know, okay? And we will work out for you particularly. And there are some other policies like the academic dishonesty and disability and drop policy. You're welcome to visit these sites if you need. Okay. So that concludes the syllabus. Okay, now let's go to the lecture. So as I said, so this course will cover some basics on the signals and systems. And we heard of signals and systems every day. And do you have some examples for signals and systems? Yeah, like typically when we think about signals, the first thing maybe we came out is the speech signal, right? So a speech signal looks like this, right? This is the acoustic pressure, and this is the time. And this speech can go to some systems, right? For example, like our cell phones. And then some other signals come out, like the electromagnetic waves for transmitting. When you are making a phone call, so you have speech coming in, and some other signals come out. So in this case, this is a signal, and this is a system. And some other examples of signals and systems, like you have objects and you have light. So you have light signal. And we are taking a picture. So this light reflection from reflected from different objects can go to your camera, and it has an image come out. In this case, this is a signal, and this is a system. So as we can see here, using these examples, so we can informally define a signal and a system. So we can see a signal is some variable contains some information, and this variable is a function of some another independent variables. Right? And a system processes this signal and has some other signals or has some behavior occurred during this system, in this system. So we could have some other signals as well. So like if we have a resistor, and we can have the voltage on it as the input. So we have voltage, and we have this circuit, and then we can calculate its current. So this is a very simple signals and systems example. And another thing we can see is, so all these signals is just a function of one random variable. So like this is a function of t, and this is also a function of t, and this is a function of voltage. It's also a function of t, time. Whenever you have a voltage, you will have a current at that time associated with this system. But in some cases, we could have a function of multi-dimension variables. So like in image processing, so we could have a 2D image, and the brightness on the pixels of this image could be viewed as a signal. So you have a horizontal dimension and a vertical dimension. So there is a brightness of a horizontal and a vertical dimension is a signal of two dimension signal. But in this class, we will focus on these types of signals, which means we mainly talk about the signal on one dimension.
It's 1 o'clock.
Maybe we will have some examples for 2D as well when we come across with them. So, and for all these signals, so we can classify them as two types, so as I will cover here. So we will cover two types of signals. So like the speech, we can see it's a function of continuous time, right? And this is called a continuous time signal. So we have two types of signal. One is continuous time, and the other one is, so if we, like, for every different time step, we have we have time 1, when t equals 1, we have a voltage, and when t equals to 2, we have a voltage. So like, if we investigate the current this way, not in continuous time, we will get a signal in discrete time, so that you have, like, this is your time step, Cn, 1, 2, 3, 4, and you have your voltage, and you have your current. So this will be a discrete time signal. And for continuous time, we have speed. Okay, so after we have the continuous and the discrete time signal, so we want to do some analysis. But the first thing is we need to mathematically represent them. So as I've already used, and we have some function, we have some independent variable, either t or discrete index n. And so in order to represent them, since it's a function of these time variables, so for continuous time, I will use x of t to represent the signal. And for discrete time, I will use x of n. So here I use parentheses, and here I use square brackets for continuous time and discrete time. So I will follow closely to the notations in the book. So you are also required to follow exactly the notations, just to make sure we don't confuse each other. Okay. So we covered the representation of a signal. And then next, so I will talk about the energy and the power of a signal. So because because in most of the cases, we are interested in some signals that contain some energy, like here, the voltage signal. And so we want to know how much energy contained in this signal for a specified period of time. So we can define the energy content in a signal. First of all, continuous time signal, we define the energy to be the integral from T1 to T2, the magnitude of this signal, square dt. And for T between T1 and T2 interval. Okay? And similarly for discrete time signal, we can also define the energy between a specified interval. Like its sum from n1 to n2 of the magnitude square on each n. For n between n1 and n2. So after defining the energy, and we can similarly define the power over this period. So remember that in general, we have power equal to the energy divided by time. Okay? So for these two cases, so we separately define the power to be for continuous time. We have, so the time interval is T2 minus T1, right? And the energy is integral from T1 to T2. This magnitude squared. And for discrete time, we similarly have energy over time. So now the time is from n1 to n2. How many times is left there? Right. So it's n2 minus n1. Don't forget to plus 1. And then this summation from n1 to n2. Magnitude squared. So this is for its specified interval, either T1 to T2 or N1 to N2. But for many signals, we may want to know the overall energy or power or average power. So like we can extend this interval to infinity to define the total energy of this signal. Okay. So we have the total energy. As I said, we can span this interval from minus infinity to infinity. So which means we have the total energy defined as when this goes to infinity, and we have the integral from minus t to t, the magnitude squared. This is defined as the total energy of this continuous time signal. And similarly, we can have discrete time signal total energy defined as, so also have n goes to infinity, and now we sum from minus n to n. So to magnitude square. So this is the total energy for discrete and for continuous and discrete time signal. So since it involves integral and sum, so some cases these integral and sum may diverge, so they will not converge to a fixed point. And do you know when will it happen? So the easiest example could be like if x equal to 1 for any n, and so this energy will go to infinity. So similarly, if we have xt equal to 1 for any t, the integral will also go to infinity. So in that case, we have the total energy is infinity. Yeah? Now, after we define the total energy, so we also need to define the average power over this minus infinity to infinity. So we can see similarly as this definition. So just remember we have the interval, time interval from t minus t here. So it's defined as still a limit as t goes to infinity. So now here it will be t minus t, so it will be 2t. And then the integral from minus t to t square over the magnitude. And this is for continuous time. And for discrete time, you can define similarly for the average power to be the limit as n goes to infinity. And the time interval now will be n minus n plus 1, so which is 2n plus 1, 1 over this, and then the sum of minus 1n to n xn squared. Okay. So we know for some cases the total energy is infinity, but the average power maybe not. Like the previous the example we showed, if xn equal to 1 for all n, and then even though its energy is infinity, but we can calculate its power. Its average power will be like, so we use this definition, as n goes to infinity, is 2n plus 1 over, so now xn equal to 1 for all n, then this will be 1. And you sum from minus n to n, and including the 0, so it will be 2n plus 1, so which means it will be limit n goes to 0, infinity, so this will be 1. You can see the average power is 1, which makes perfect sense since we already defined that the xn equal to 1 everywhere, right? So for some signals, this total energy is not infinity, right? Because one easiest example is if this signal has a finite duration. Like for example, so if I have this signal here, this is t, and so it only has like xt only has finite value when t is less than some constant c and 0 when elsewhere. And then we can easily see the integral of this signal using this definition here will be the area of the triangle here. So it's finite. And if the energy is finite, what about the power? So we know the energy is finite. What about the power? Since the power is over infinite time period, so we can easily see the average power will equal to 0. And this type of signal, we call it as energy signal. Okay? And like the previous example, we used this signal, so we know this is infinity, but the average power equal to 1, which is finite. So we call this type of signal as power signal. So in general, we can see that if we have a finite energy, total energy, and there will be guaranteed the average power will be 0, because the average power will be examined over the infinite time interval. And of course, there exist some cases that both energy and both total energy and average power is infinite, right? Okay. So next, to better understand the energy and power for a signal, so I will give you a exercise, and using this example, it will be not difficult for you to work out. So get a piece of paper, and I will show you this example, and after you finish, we will go over it again. So define this xt equal to 4 minus t squared when t is between minus 2 to 2 and 0 else. So you need to calculate its total energy and also the average power. So you will get the idea of how to calculate the total energy. Okay. So now we will see how to calculate the total energy for this signal. According to the definition, so it's limit t goes to infinity. And the integral from minus t to t, the magnitude square, which is equal to the integral from minus infinity to infinity, right? And substitute in this signal. So let's first leave xt here for a moment. And the next step, so since it's 0 after, before between minus infinity to minus 2 and 2 to infinity, so which means the integral during that time period will be 0. So we only need to integral between minus 2 to 2. means we only need to integral over this time period. And now we can substitute in this this signal here. So we have 4 minus t square dt. And then next, so we can expand this signal formula as 16 minus 8t squared plus t fourth t to the fourth dt. Okay. And now you just look at the expression, whose differentiation is this expression. So it's 16t minus 8 over 3 t squared, sorry, t cubed plus, so this will be, yeah, 1/5 t to the 5. And then you evaluate at 2 and minus 2, use this one minus this one, and you get the answer. So the final answer is 512 over 15. Okay? And since the total energy is finite here, so we can easily see the average power is 0 for this signal. Okay. So that handles the energy and the power. Okay. So next, I would like to talk about the transformations on independent variables of a signal. So, because in many physical systems, like the delay registers, they usually put some delays on the input signals. So that's why we need to learn some basic transformations on the signals. So we will touch these transformations later when we talk about the systems in details. But now we just focus on some very basic transformations. And so the first thing is time shifting. So suppose I have a time shifting. Okay. So suppose I have a signal xt, and probably let's deal with this triangle graphical representation, and I want to shift by td. So what will it be? Okay, so like then in mathematical format it will be t minus td. So which means if you have 0 here, so you will redshift the signal with the same shape, but now the 0 points and all the other points are moved to td now. So it will be like this. Okay. So it's not equal. Let's make it bigger. Okay. Now they look have the same shape. So similarly for discrete time, if you have xn signal and you want to shift by n0, then you will have n minus n0. So n0 is an integer as well. So suppose we have 0, 1, minus 1. So we have this signal, and we want to move it by, say, 2. Okay? And then what will flag. So you move all the points to the right by 2 and with the same shape. So in that case, the -1 point will become at 1. Okay. And the 0 will be 2. And then 1 will be 3. So this is we move to the right-hand side. And of course, when you have plus some positive number here, which means it's minus a negative, which means you move to the left. So you can work on that for this example. Suppose I have xt. I have a sinusoid equal to sin t. And for t between -pi and pi, just one period, and you can move it to td equal to minus pi over 4. What is the moved signal? So mathematically, so it will be xt plus pi over 4, right? And then you substitute is sin t plus pi over 4. And then you move this shape to the left by force of the period. So which means now this is your 0. Okay. This is the time shifting. And next property I will talk about is called the time reversal. So, like if I have a signal xt, and it's reversal. So since it's called reversal, which means I have x minus t as the reversal of this signal. So again, if we have a signal like this triangle, and then its reversal will be reflected by the t equal to 0 point this axis. Right? So which means it's it will look like this. And similarly, if I have a discrete signal xn, then its reverse is x minus n. So like if I have this signal here, I'll use the same example. And the reverse will be like now the value at n equal to 1 will be at n equal to -1. So similarly for this -1, it will become this one. So it's just reflection. So this is not difficult to understand. Okay, so now we talk about time shifting, time reversal, and next I will continue with the time scaling. Time scaling means you put some scales on the independent variable of the signal. So here is 10. And for example, if I have xt, and then I want to see x2t or x half of t. So we will see how this scale will affect the signal. So suppose we still use this one. Suppose we have xt here. Maybe I should put some values. This is -2, this is 2. And what will it be like for x2t? Okay? You can see, so when t equals to 0, it's x0. So same value here. And when t equals to 1, it will be x2 now. Which means when I have x1 here, I've already reached this value, 0 here. So similarly, when I have -1 here, I reach the other point. Which means I have a shrinked version of this signal. So when I have the scale is greater than 1. So, and now if what if we have a scale less than 1? Let's see. So we have when t equals to 0, we still have the same value here. So this is a fixed point. And we want to reach this point, we need t equals to 4, right? So which means we have t equals to 4, and similarly we have -4 here. Then we have a triangle like this. So it's kind of stretch the signal by factor over 2. So similarly, we can see for discrete time signals, they will be a little different. So let's see, use this signal. We have xn, and we have this signal -1. We want to see x2n and half of n. Let's see. So if we only have this one, okay, when n equals to 0, it's the same value here. When n equals to 1, it's x2. x2 is 0. Okay. Which means we have here. And similarly for -1, we'll have 0. And all the other values will be also 0. So this is x2. As some of you maybe already know that this is actually a just to pick some points, pick some values through this sequence. So it's, you can call it a sampling. And for this one, okay, for n equal to 0, we have the same value here. But for n equal to 1, we have x over half. But we haven't defined a discrete signal with non-integer values. Remember, here our discrete time signal are all integer steps. So for this case, we will not consider at this moment. We will talk about this later in this course. How can we handle this when equal to 1 and x half? So, but we have xn equal to 2, it's equal to x1. Okay? And similarly, when n equal to -2, we have this value. So it's still like stretch the signal a little bit, but just with some undefined values between the new signal. Okay. So after we define these three transformations, and we can summarize it. We can generalize the transformations to be like xt, if we have xt, and then we can have x of alpha t plus some beta. So this reflects the time shifting, right? So here, time shifting. And this reflects the fact that the time scaling. And so since this value can be, so here we just use the positive values, for example, and actually we can have some negative values as well. Just if, so suppose if we have a -2 here, so just do the reverse first and then do the time scaling. So here we can see for general case, so this can be a positive or negative. And okay, and so we will use an example again to illustrate the general transformations. So just to make sure you understand every step. So we will use, so this is xt, and for discrete time we will have x plus so I will give you an example. So suppose we have a continuous time signal, which is defined as xt equal to 0, when t is less than -1, it's -1, when t is between -1 to 0, t squared, when it's between 0 to 1, and 0 and 1. T between 1 to 2, and for 0 greater than 2. Okay? And you are required to calculate the x of minus half t plus 1. So you will first need to plot the signal and plot the signal for this one as well. I will give you like how many minutes to it? Maybe 10 minutes to work on this example, and then we can go over the solution. Okay, now let's see the shifting of this signal to this one. So first we need to plot this signal. So it's t 0, 1, 2, -1, -2. So t is 0 for the left hand side, t is -1, t squared or 0 to 1. And 1 for 1 to 2. And 0. And to get this signal, so we can see we first need to shift this signal by 1. Right? And to the left hand side. So we first get xt plus 1. We will shift this way. Next 1, next 2, 1, 2. Now you have this signal. Here. Okay. So this is xt, now this is xt plus 1. And then to handle this part, so we need to reflect and then stretch. Let's first do reversal. So it will be this one. And then next we need to stretch this signal. So it will be -2, 0, 2, 4. This one. This is a way to get this transformation done. That's from here. So is there any other way to get the same answer, but use the investigation of this expression? So we can see it's equal to x of minus t minus 2 together, right? And what does this mean? So we should be equivalent to this transformation and get this answer. Okay, so we will just double check with. So you need to reflect the signal and stretch, so which means this is 0, this is -2, this is -4, this is 2, this is 4, and then you will have. Okay, so this will be the x as half of t. And next, we will shift to the right hand side by 2. Okay, so if you shift this, because this is only 2 minus 1, right? And now you shift this signal to by 2. You can see it gives you the same solution here. Okay? So just pay attention that the order, because like if you confuse with this with the parentheses, but actually that's totally different. Scale. Okay, so due to the time of this lecture, so I will end here. So today we covered, we introduced the signals and three basic transformations on the independent variable, which include the time shifting, time reversal, and time scaling. I will pick important basic signals for the sinusoid or complex exponential signals. Okay, thank you.